So when they trained the original GPTs, and you train it on internet data, there's a lot of unsavory content, and this is how I'm going to put it, on the internet, right? And it doesn't matter your political leaning. There are things that are really immoral and really bad. And some of the earlier chatbots parroted that because, again, one thing that these things do is they overfit quite heavily to their data. Again, when you make more parameters bigger, as you said, it gets better at memorizing the data and the noise in that data. And it's a principle called overfitting in machine learning. And so if you give it all of the internet, it's going to be very good at becoming an approximate, I'm not going to call them this exactly, but lookup tables, right? And they can learn to kind of patch together these different pieces of information. But at the end of the day, they can parrot anything. And there's a lot of things they can get to that we don't like. So those unsavory parts of the internet, what we do is we constrain them with guardrails, and we have humans go ahead and we have them interact with them and traumatize them deeply, is what we had found out from some tech companies that had offloaded some of this crowdsourced labor in other nations. And I'm trying to be as vague as I can here without making any direct attacks, as I don't feel interested in engaging in that. And these people were traumatized, but what they did was they were able to say, oh, we probably don't want it to say this, and this is bad, this is good, this is acceptable, this is unacceptable. And then they can encode these constraints to prevent the system from saying these unsavory or going down these unsavory paths that the internet gets you to. So what we do is we heavily engineer guardrails to kind of tailor the experience, because there's a lot of marketing that goes into these transformers. Rather than, you are right that you can train it on more things, but I think training on more things risk also polluting it with, again, since we're aggregating across all of humanity, right, you're going to start getting things that might not be what you want. And that's part of the effect of the hallucinations, but it's also why, for example, these things give you nonsensical answers. Like more semi-recently, the people were like querying Google's engine or its chatbot, and it was starting to give them Reddit answers to their questions, like how to make certain foods, and it was saying we should put glue in it. That would be a very good ingredient, right? Why? Because these things also get attached to very salient pieces of information. So there's a particular kind of information or the perspective on the internet that's going to be very emphasized. It's like a weight, right? A probability in the model itself. And so the only way that you can counter it is kind of what I was saying for modal computation, where we need to encode biases, but I think those come from evolutionary processes. We encode our priors by saying if statements, right? And we kind of like prevent it from saying certain things and checking it. So the capacity argument is part of the story, but we end up having to do a lot of engineering to prevent them from devolving.
Well, that's really helpful, because I mean, part of the reason, so you kind of, talked about their flaws there, but I kind of wanted, because like a reason I brought them up again is actually, I wonder if you can say that mortal computers will be more efficient and more effective and be able to do the kind of things that these LLMs can't. But then I think about people talking about, well, maybe these LLMs would get to like some kind of super intelligence. So hey, they're super inefficient, but if the people that make the most, they turn the internet to such a degree that they, I don't know, find the secrets of the universe, etc., then they won already. I don't know. Tell me about that. I mean, and as well, other things hidden, maybe even in language itself, like that they can have some kind of understanding that we don't realize, or we think it's just the internet. Tell me a bit more about that.
Well, okay, there's a lot of different pieces to your comments and questions there. I would say, I guess to kind of tie in our last discussion about bigger is better, which is a typical argument. And without the poisoning argument and the data problems and the hallucinations I was explaining, there is an argument that the bigger these systems become, the more likely they're going to solve problems. They're going to become AGI, right? Artificial General Intelligence. And I think that's a little nonsensical, because while the brain is composed of billions of neurons and trillions of synapses, so there is that kind of scale of complexity, which is needed, you have to look at the individual computing units. And I think that's the problem that I have with deep learning in general is that even our neuronal models are pointwise, right? They are just literally weighted sums of incoming signals, and you chuck them through a little function, a nonlinear function, to give it some nonlinear behavior, and we learn the weights along those incoming edges. And it's gotten us pretty far. I mean, we have some really nice applications. Again, just a comment, there's not like it's useless. But these computing units are so unbelievably simple. And I think that that's the inherent reason why you need more and more to get the generalization that you want. It's like this inefficient use of your capacity, because I think of cognitive science, which has this premise of building cognitive architectures. And what is a cognitive architecture? It is a theory of mind. Now, again, it is a theory or a hypothesis, and it can be wrong, and many times they are, but such as science. But when you have these architectures and these particular modules interacting with each other, you are trying to ground them in known memory mechanisms, for example. And you are building a parsimonious architecture that tries to get that functionality that you want in an efficient and grounded kind of way, whereas a lot of connectionist is what they used to be called. Deep learning architectures today is, if I just do more, I can somehow learn different tasks. And they do, right? Actually, there was a really interesting discussion at, I believe it was AAAI, the keynote that I was at, where the guy did an experiment where he built a little transformer, and it didn't do well at all. It failed on most of its experiments. But as it gradually increased its complexity, that means more layers and more neurons, there was like this point where it reached like 1 billion, and all of a sudden it could start doing many tasks in a row, which was really interesting. There was like, it needed that complexity scale. However, and of course then he said, so that's why bigger is better, and we need way, 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 way more, and then we can just like learn everything that a human can, or all of humanity. But the way I look at it is without any bias, and cognitive architectures have this beautiful bias, which is modularity, right? We kind of have specialization. We humans, when we design a cognitive architecture, we're playing the role of evolution. We are saying we're going to skip simulating many millions of years of evolution, and we're just going to get to the result that we're like, well, okay, this entity seems to work really well. Let me encode long-term, short-term types of memory, procedural, declarative, and wire all these together. And now that inductive bias means I don't need to build billions of parameters, and I can emulate a whole variety of tasks all in one architecture. Whereas the connectionist paradigm today doesn't even embrace too much. There is some of that, and I want to be careful not to say there's nothing. That modularity, those inductive biases, the efficient use of parameters. And I think mortal computation kind of takes it all back and says, what if we were to build the simplest possible circuit to attack a problem? You can get really good performance, even from just one task performance, with more biophysically accurate neurons and spiking neural nets, because my lab works on those and does all kinds of stuff with that. While they're not perfect, and there's a lot that you can criticize about them, they are naturally able to encode temporal data. Whereas in deep learning architectures, with those little neurons that I was explaining, those pointwise neurons, it's very difficult. And that's why transformers exist, because we're just like, we can't do time, so we're going to give it windows of data and chuck it all at once, and that's why they can kind of do temporal-like things. But we're kind of omitting a lot of the biological mechanisms that allow us to efficiently learn from and process in an online way temporal data. And this is, by the way, this is just one of many things. And what do I mean by online? It means you and I, when we train, we update every millisecond of our lives, right? It's not, and again, things can change with different timescales, whereas like deep learning, what you would do, and this was specifically even before transformers, you would take a sequence of data and you would unroll the architecture, copy it over time, and calculate the derivatives to update it. And the joke I have when I teach my students, older deep learning things, is I explain that this would be like you copied your brain several steps in time in a time machine, stitched all your copies together, updated it, and then rolled them back in, and you rinse and repeat every step in time, which is nonsensical and inefficient, and also runs out of memory on computers. Biological entities can operate iteratively online and with very little capacity. So imagine if you could get what you do with transformers with very few neurons, very few subcircuits. Now all that capacity of billions and billions of neurons that we use for transformers could be used for other things. And imagine the complexity of tasks that we could do, not just an array or a suite of tasks, but now we can aggregate subtasks together to do even more complicated tasks. I think if we wanted to get towards even any remote sense of AGI or general intelligence, we sort of need to revisit the fundamental computing units that compose these architectures. And I think biology gives us one very promising place to look to how to build those very powerful and rich computing units that then you could build very complicated architectures from.